chemistry book, and we're in chapter 5, and we're in section 3. We're going on to the different laws that apply to gas. And so now we got to the part 2. We're going over these different laws, and there's the combined gas law. And as you recalled, we basically are taking Charles' law and Boyle's law and combining them both so that we have an equation. So we basically have the equations with volume, pressure, and temperature. So this would be the equation. As for pressure and volume here, because they are indirectly related over temperature. So you just really need to know this. P1 V1 over T1 equals P2 V2 over T2. And you can use this combined gas law to combine all of them to, if you have a problem, to do. So let me see if I can go on up here and see. The only other thing you need to know, too, with the combined gas law is, since this part is very important because it'll be a test question probably, since both temperature and pressure affect gas volume, it is often convenient to relate volumes of gases to a set standard conditions. We call this standard temperature and pressure, and it's STP. So if you have this initial STP, you're going to know it means standard temperature and pressure. So what is the standard temperature and pressure that they're going to talk about? Well, the standard temperature is going to be 0 degrees. We're going to find 0 degrees centigrade. So what's 0 degrees centigrade? Well, we have to change it to kelvins. Remember, it has to be absolute 0. So basically, to change centigrade to kelvins, you just add 273.15, and then you'll get your kelvins. And then the temperature here is 1 atm, which is 760 torr. So as a test question, you can say, what is your standard pressure? It's going to be 760 torr or 1 atm, or it's going to be 0 degrees, or it's going to be 273.5 kelvins. Although standard temperature is 273.15, exact number, most of the exercise in this text will be used as standard. They're going to round it 273 to sig figs. So basically that's the standard temperature, okay? So now we just have equations to figure this out. The reason we're combining because we're going to have equations. So I'm going to put you on my notes as I'm doing these questions here for the combined gas laws. You think you have them up here. So basically the combined gas laws, we're talking about volume, temperature, and pressure all together. And so basically we have PV over T equals K, or P1 over PV T1. So this is the combined. Just have to remember this. This is going to be a formula that you need to know. So you're going to use this formula when you're doing any kinds of problems, okay? So now we're going to have this problem with methane gas. The problem says, let's put it down here so you can see it better. The problem says a sample of methane gas occupies 5.00 liters at 730 torrs and 27 degrees centigrade. What volume will it occupy at 1 atmosphere, which is 760 torr, when cooled to the temperature of dry ice, negative 78 degrees. So it looks like a complicated thing, but all we have to do in any of these problems, and you'll have them on the test, is to make sure you put them all into the right category, whether it's P, V, T, so algebraic at least. So here. So we know that liters are pressures. So basically the initial pressure T1, are volumes. I'm sorry, I said pressure. So 5.00 liters. Volume is a liter. That's how much, like if you have a Coke that's a liter or whatever, that's a volume. So the volume is going to be 5 liters. The pressure is going to be 730 torrs. So I put that, 730 torrs for the pressure, and then 5 liters for the volume 1. And then the temperature is going to be 27 degrees centigrade, right? And so now the other volume here, what volume at 1 atm cooled. So right here with the other one we have PT is going to be, we're going to know that volume is going to be 760 torr, the volume, we want to know the volume. The pressure is going to be 760 torr, and then the temperature is going to be minus 78 degrees centigrade. Okay, so looking at the problem, there's a couple of big things we need to do. We found all of this, but we have to change centigrade into kelvins. That's number one, because we cannot use centigrade because it's not an absolute scale. So negative 78, we're going to add 273 degrees and we get 195 kelvins. So that's easy enough. So now we know what that temperature is. So that's the first thing we must do. And the next thing we must do is we have to fill in all of these. P1 V1 over T1 equal P2 V2 over T2. So we do that. So we put in 730 torrs, P1, right there. 5 liters, V1, right there. We put in this 27, we had to change 27 degrees. We changed this to 195 degrees, but we forgot to tell you that we changed 27 degrees. We added 273 and we got 300 K. So now we're going to say put the 27 degrees is 300 K, which is 300 kelvins. And then we put over on this side, as we change this together, PV to T, because we're looking for this volume. So if we're looking for the volume, we put T on this side right here, and we put P on this side. So basically these two things. So we have volume here, so that we're going by this here now. So P, 730, volume is 5 liters. T2 is going to be this one, which is going to be 195 K because we changed it to kelvins. And then divided by T1, which is 27 degrees, but we changed that 27 degrees to 300 kelvins there. And then P2 is 760 torrs. So we just filled these in right here, all these in. Now you get your calculator out. You can cancel out the kelvins and the torrs because it's going to be in volume, which is liters. So you say 730 times 5 times 195 divided by 300 times 760. You got to do this on your calculator and you'll get 3.2 liters. So we look up here, and what we're looking for, the methane gas at 5 liters, we want to know when it's cooled what the volume is. The volume's going to be 3.2 liters, as the volume. So this is because we have a combined gas law of all 3 of these. So all 3 of these, we're going to use this here, which I use down here, and just fill in these blanks and then use your calculator. So it's not that hard. Okay, let's go on to the next. Let's see where we're at. Okay, let's go down to the next. So in your book, going down to Gay-Lussac's law, and we'll find out what's Gay-Lussac's law. So we're going to talk about some laws. We're going to talk about Gay-Lussac's law and Avogadro's law and the molar volume at this point in this section, this last section. So let's look in your book here. Okay, so here we have Gay-Lussac's law. Is in 1809, Joseph Gay-Lussac found that when gases reacted, their reactant volumes measured at the same temperature and pressure were in ratios of small numbers. So what does that have to do? Because now we're going to talk about molecules, and somehow they're in relationships of small numbers. So when he was doing this, he found the gases did this. Gay-Lussac did not know the formulas of the gases, which he studied, and so he didn't know how to write equations or anything, but his observations were important because they would develop further on atomic and kinetic theories. And so these are summarized in what is known as Guy-Lussac's law of combining volumes. So Guy-Lussac's law of combining volumes, when measured at the same temperature and pressure, the ratios of the volumes that react are formed as small whole numbers. So the reason the small whole numbers are important is because now he's talking about molecules. And it's kind of weird. He thought, what do these small whole numbers have to do with anything? Well, Avogadro was figuring it out. So in 1811, 2 years later, Avogadro, who was a friend of his, a scientist, his name was Count Amedeo Avogadro. And he lived 1776 to 1856. So, and he's in Italy. And he explained Guy-Lussac's observation in terms of molecules now. Because remember, Guy-Lussac didn't know anything about molecules or what was going on with molecules. So now he's going to explain it, that it has to do with molecules. So here's a picture here. So Avogadro's law there, as you see. Avogadro's law says equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. This law holds for any gas, no matter what its composition is, but not for liquids or solids, of course, but for any gas. So look at this picture. So the picture basically is saying we have a gas argon, and it's at the pressure of 760 torrs. They're all at the same pressure. And now the volumes, they're all at the same volumes. But what about the molecules? Are the molecules the same? Well, we have 3 different types of molecules here. We have argon, we have carbon monoxide, and we have methane. Those are all different molecules, you know. But if you count at that volume, these molecules, they're all going to be the same. There's going to be just as many molecules as there are in argon, as there is carbon monoxide, as there is methane, or any other type of gas. So all gas molecules, equal volumes of gases at the same temperature and pressure there, contain equal numbers of molecules. So all gases have equal numbers of molecules. That is pretty cool. That is kind of like what God would say, is he's holding everything together, but all these different gases have the exact same number of molecules at any given volume and temperature. So that really helps us in figuring out a lot of different things. So just know when you have a test question that Guy-Lussac, basically he was saying combining volumes, he found they were in small ratio of numbers. So he's like, what is going on here? And then Avogadro found that all of the gases had the same number. So basically, Guy-Lussac knew they were, when combining volumes, they were small whole numbers, but not that they were exactly alike. And here we find out that they are exactly alike. So that is pretty amazing. So in doing this, Avogadro's law was explained in terms of the kinetic energy. So basically this has to do with kinetic energy in these volumes too. But let's go up here what we're talking about next. We may mathematically state Avogadro's law, and it's going to be V is proportional to N. So now we have before we had volume, we had pressure and temperature. Now we have N. So what is N? So V equals Kn constant tension. N means basically the number of moles of gas, which have to do with the number of atoms of gas. So thus we expect equal numbers of moles of gas to have equal volumes, right? N1 equals N2, N1 equals N2, all of these they're equal volumes. So N is just going to be talking about moles or atoms. So whenever you see the N, it's going to be talking about that. And then on to this molar volume. The volume per mole of gas under specific conditions is the molar volume. For gases that behave very close to ideal, the molar volume at STP is the same. So STP is standard temperature and pressure, is the same at 22.4 liters per mole. This value allows us to relate to other gases now and everything. So remember, this value applies only to gases though. But here's a picture of it. So if we want to find 1 mole of gas at STP, any mole of gas is going to be at this, we're talking basically as we talk at the STP, standard temperature and pressure, is going to be 22.4 liters. This is about 22.4 liters. When you're thinking of a liter of cola and liter of this, but we're going to be 22.4 liters. Okay? Just remember that name, 22. Recognize it on a test. If it says a molar volume, you're going to say 22.4 liters. So, on to the next. And then we're going to talk about ideal gas law. So before we talk about the ideal gas law, let's go over this a little bit in my notes here so we know. Just a little review of this. So Guy, it says Gay, but you pronounce it Guy, I think. Guy-Lussac's law in 1809 of combining volumes. When measured at the same pressure and temperature, the ratios of the volumes of gases that react or are formed are small whole numbers. So he was basically saying, man, you know, these ratios between them are very close to being equal. And Avogadro's law basically said equal volumes of gases at the same temperature and pressure contain equal number of molecules. And so this law holds for any gas. And so then down here, trying to figure out, let me move this up so you can see. So now if we're trying to figure this out, we can have basically have N representing the number of moles of gas for 2 different gases. And we found that the 2 different gases, the molar volume of it is going to be what? Because all of them are the same. It's going to be 22.4 liters per mole. Okay? So that's about what you need to know for that. Now we're going to go into, see if we have time, let's go into the ideal gas law. And this is going to be combining everything. So it's a little hard because it's combining everything, you know, into a formula and then using that formula and putting all the different pieces of the formula together to find one. So basically, as the ideal gas law says here, the ideal gas law is a combination. Let me see if I can pull this up a little more so you can see it better. There we go. The ideal gas law in combination. It's going to combine Boyle's law, Charles' law, and Avogadro's law. Those are the 3 laws that we learned so far. We did have the Guy-Lussac's law, but he didn't really have a law. He just had an observation. So here we have using, and we have that volume now because of Avogadro's using 22.4 liters as the volume. And so this is basically, I could go through this whole thing as I did in your book, and you can go through it, but basically you need to memorize this formula and this number here. So to memorize it, R equals PV over NT. So you have 1, 2, 3, 4. Pressure and volume and molecules, which are moles and T. So whenever, let me tell you, whenever you're talking about moles, you're going to talk about the ideal gas law. If somebody's asking you for a question, how many moles and everything, well, you have to go to this law, right? Are going to the combination. So especially when you have this, but we have right here that R, what is R? R is going to equal 0.0821 liters. So this is what we found out. This has been figured out for you already, so we don't have to go. So the ideal gas law allows you to calculate any of these 4 variables to find the pressure, to find the volume, to find the temperature, to find the N, which is the number of moles, and 1 mole ideal occupies 22.4 liters. We already knew that one. We found that out because all of them are the same. So now we're going to do the equation. Basically, you need to know that formula to do the equation, right? So so the equation is what pressure will 0.025 moles of oxygen exert in a 400 milliliter flask at 25 degrees centigrade. So how do we do this? So here we have volume 1, first volume. Volume's going to be in milliliters, 400 milliliters. So we're going to have to change this to liters because it has to be in liters. So anyway, we changed it, 400 milliliters, you change it to 0.4 liters, right? Just by changing that, milliliters to liters. So that's the first thing we have. Now we have N. What was N going to be? Well, N is going to be 0.025 moles, okay? How did we get that? Well, basically figuring the moles of N right here, 0.025 moles. So we put that down here. So now we need T. T is going to be 25 degrees. Well, we have to have it in the absolute scale. So we add 273 to 25 degrees centigrade and we get 298. So now we have the volume and we have the moles and we have the temperature. So now we can solve it by the ideal gas law. So let's pull this up so we can see. So here's our ideal gas law. P equals RNT divided by V, right? Solved by the ideal, here is our R equals, this is the one we memorized. R equals PV over NT. R equals pressure, volume, moles, and temperature, right? But we're going to look for pressure. So if we're looking for pressure, pressure is going to equal, well, we're going to have to basically put volume on the bottom, which I did here, because we're going to put volume over here. So we move the volume over here, and the NT is going to be at the top. So it's going to be RNT divided by volume is going to equal pressure. So now since we're looking for pressure, it's not going to be R equal, it's going to be P equals RNT over volume, okay? So then we put in all these values. First of all, we know R is going to be 0.0821 liters. This is just known. R is always the same. It's always that. The N is going to be up here, 0.025 moles. See where I'm at here. Okay. And then on to, we changed the temperature of 25 degrees to 298 Kelvin. So we put that here for temperature. So we have RNT. And we're going to divide this by the volume, and the volume is 0.400 liters. We have to go by liters because R is always in liters. So we always have to change this to liters. So we did. So now we get our calculator. First of all, we can cancel the liters here, cancel the liters here, and then you can cancel, because it's K and mole, you can the K and the K here you can cancel, and the mole you can cancel, and the K you can cancel here because it's that's part of the equation. So here we just have to multiply this number by this number by this number, you know, and then we're going to divide it by this number. So, and then we're looking for the pressure, so it's going to be ATM or in torrs, but they want us to put it in ATM, I guess. So basically, as we did this on your calculator, this times this times this divided by this, you get 1.5 ATM. So the pressure that you're looking for is going to be 1.5. So I have here to always memorize this, and you'll be able to do these hard problems. R equals pressure volume on the top, because that's just like pressure and volume on the top is kind of like Boyle's law. What is Boyle's law? Temperature's on the bottom because basically temperature is going to be directly, so temperature is going to be in the bottom, and the N is going to be on the bottom too. So we have pressure, volume, moles, and temperature like that. And then we can, if we're looking for any of these, we can find out just like I did up here, just like I did up here when I was looking for, let me see. Just like I did up here with the pressure, and I changed it to find the pressure. You can find any of them. You can find pressure, you can find volume, you can find the moles or the temperature, you can find anything, any of these. And then you have to know what, basically what R is. Right here, when you fill in what R is going to be 0.082, 0.0821 liters of ATM over K mole. So we're going to fill that in. Wherever R is, we fill that R in. So you need to know that. So that got kind of complicated, but that's the end of that. And that's probably the hardest one you're going to do. And we'll go on to the next section, which has to do with diffusion.